Alright, so we're going to be working with systems of linear equations. So this is going to be a setup where we have two equations and two unknowns, and we have to solve for two of the unknowns. So maybe we might have a situation where we know two adult tickets were sold. And one child ticket was sold for the sum of $32. We might also know that one adult ticket was sold and three children tickets were sold. Three child tickets for a sum of $36. And we want to know the price of each ticket. So first we're going to transform each of our bits of information into equations. So 2a plus 1c equals 32. Similarly, 1a plus 3c equals 36. So now we have two equations and two unknown variables, and we want to solve for each of those variables by themselves. The way that we do that is we first look at one of our equations. So pick equation, any equation. Let's do equation 1. And we're going to solve for either variable. So A or C. I'm going to solve for C. So 2a plus c equals 32. Then c equals 32 minus 2a. Now that we know that c equals to 32 minus 2a, we're going to plug this in for the c in the other equation, and then we'll have one equation, a plus 3 times 32 minus 2a equals 36. And now we have one equation with only one variable in it. And then we can solve for that one variable. So let's solve for that a variable. So first let's distribute this 3 into the parentheses. So a plus 3 times 32, what is that? That's 96 minus 6a equals to 36. So we're going to get minus 5a if we combine all of our a's on the left-hand side of the equation. If we minus 96 to both sides, so minus 5a equals to 36 minus 96, what is that? Negative 60. And then we can divide both sides by negative 5, and a would equal 12. Or more specifically in our case, $12. So that's one variable, and we want to solve for this other one too. We want to solve for c. So the way that we can solve for c is that we know a, we can just plug in a into either our original two first equations, and then we can solve for the c variable. So if 2a plus c equals 32, that's the first equation, all we're going to do is 2 times 12, because we know what a equals to, plus c equals 32, 24 plus c equals 32, and then we subtract 24 to both sides, and c equals 8, or more specifically $8. So what does that tell us? That each adult ticket is worth $12, and each child ticket is selling for $8. So that's one way that we're going to be dealing with two equations and two unknowns. And that's how we do it when they're written in standard form. We've got all variables on one side of the equation. Is that we got to solve for one of our variables and then plug that into the other side. So another situation we might be dealing with is a classic economic situation where we know the demand function for a good could be the price equals to 16 minus 2q, and the supply equation is P equals to 2 plus 2q. Now let's look at this. This isn't written in standard form. We don't have all our variables on one side of the equation. As a matter of fact, both equations are solved for P. So if we have P equals this, 16 minus 2q, and we also have P equals another thing, 2 plus 2q, Well, we can just set both p's equal to each other, or set both equations equal to each other, so to say. And we're just going to be left with 16 minus 2q equals to 2 plus 2q. And now we can solve for our q. So if we add 2q to both sides and subtract 2 to both sides, we're going to be left with 14 equals to 4q. Divide both sides by 4, and 3.5 equals to q. So once again, that's going to be our q that we're interested in. To solve for the p, well, we can just plug that 3.5 into either our original equations. So let's plug it into that demand equation. So p equals to 16 minus 2 times what we know q to be. So p equals to 16 minus 7, or p equals to 9. And those are equilibrium things. So if we were to draw a funny little graph, we have our price axis, and we have our quantity axis, we have our demand curve with the price intercept of positive 16, we have our supply curve with a price intercept of 2, and we know the intersect of this is going to be 3.5 and 9. So we will know where those two equations equal to each other. All right, let's do another one of these supply and demand type situations where we have the demand is P equals to 100 minus 2Q, and supply is P equals to 10 plus Q. So note, both equations are written as P equals something and P equals something else, so we can set that something to equal something else. So 100 minus 2Q equals to 10 plus Q. And we're going to want to solve for that Q now. So let's subtract 10 to both sides, add 2Q to both sides, and we get 90 equals to 3Q. We divide both sides by 3, and we are going to get 30 equals to Q. And we are going to denote that Q star when we talk about economics, because we're going to be calling that the equilibrium quantity. Alright, so we can plug that 30 equals Q into either of these two equations. This one looks like a little bit easier to work with because we don't have to multiply our Q value by anything. So P equals to 100 plus our Q value, 30. So P equals to 40. So that's our price equilibrium. So we know the quantity that's going to be bought and sold in the market, and we know the price that's going to be bought and sold in the market. And that's because we know the equation for the demand curve, and we know the equation for the supply curve. We can plot these two lines on our graph. We have our supply curve that had the price intercept of positive 10 and a slope of 1. And we have our demand curve that had the price intercept of positive 100 and slope of negative 2. We solved for the equilibrium already, which was 30, 40. So that was the quantity, and this was the price. Alright, that does it for today.